Ladies and gentlemen, welcome to my presentation. My name is Axel Kansy and I am a research associate at the Fraunhofer Institute for Structural Durability and System Reliability in Darmstadt, Germany. My topic today is the investigation of the statistical and geometrical size effect on the fatigue strength of EN GJL 300 under consideration of the graphite morphology. This investigation was carried out in cooperation with the Foundry Institute of the RWTH Aachen University in the framework of the Optigus research project. Let us first take a look at the motivation and aim. The design of large-scale components with regard to fatigue strength is based on specimen tests, which have a significantly smaller volume compared to the component. In order to transfer the fatigue strength of the specimens to the component, it is necessary to take into account the statistical and geometrical size effect. Three samples of different sizes are shown in this image. The larger the specimen, the greater the number and size of defects in the highly stressed volume. So we can see here the highly stressed volume and the number of defects, and the size of the defects increases with an increase of the volume. And a higher number of defects leads to a lower fatigue strength, which is indicated here below. So the statistical size effect is based on the fact that the probability of having a critical failure defect in the specimen increases with increasing of the highly stressed volume. In the study, the highly stressed volume is defined where the maximum occurring stress is reduced to 90%. The determination of the highly stressed volume will be shown on the next slides. Notched specimens are used to obtain particularly small highly stressed volumes. Here, however, a geometrical size effect comes into play in addition to the statistical size effect. The geometrical size effect takes into account the macro support effect due to the occurring stress gradient, which you can see here at the notch, so that the material can locally withstand higher stress amplitudes. The aim of the study is the investigation of the statistical and geometrical size effect on the fatigue strength of gray cast iron to enable a transfer of the fatigue strength from small-scale specimens to large-scale components. The gray cast iron grade we investigated is EN-GJL 300, also known as GG30. The material is based on serial component and cast samples. The chemical composition for the component and the cast samples is shown in this table. Beside differences in the silicon content, we see difference in manganese and scandium. Let's take a look at the microstructure by using light microscopy images. We can see slight differences in the graphite morphology. So in this microstructure, the lamellars are a little bit more dense compared to this microstructure. By comparison with the sample images shown on the right side, we can classify the graphite arrangement. And we see that this one here, type A, fits best to our microstructure. It can be stated that despite minor differences in chemical composition and the graphite morphology, the materials compare very well with each other. For the fatigue test, we used three different specimen geometries. A large specimen with a notch factor of 1.05 and a highly stressed volume of 3,240 cubic millimeters. A small specimen with a notch factor of 1.06 and a highly stressed volume of 378 cubic millimeters. And then we used a small specimen with a notch, which you can see here, with a notch factor of 2.84 and a highly stressed volume of 0.1. So we can see by using a sharp notch or a specimen with a sharp notch, the highly stressed volume can be drastically reduced. The determination of the highly stressed volume was carried out by FEM simulation via Abacus. Here you can see the simulation result for the small unnotched specimen under axial stress. This area here shows the highly stressed volume down to 90%, and the colors indicate the amount of stress. The black area defines areas with stresses below 90%. For the notch sample, the stress is also indicated with different colors. We see a strong stress concentration in the notch ground, and the highly stressed volume down to 90% is indicated here with the red colored area. And we can see that it is only a small fraction of the highly stressed volume compared to the unnotched sample. For the investigation of the fatigue strength, specimens were removed from cast samples and a component. Here you can see a picture of the cast sample, and here the dimensions. We have here a wall thickness of 75 millimeters. The upper part is only used as a feeder, and the specimen were removed only from the lower part. And here you can see how the samples were located in the cast sample. The components we used for the investigation was a gearbox housing. Unfortunately, I'm not allowed to show you a picture of this component, but to get an impression of its size, the dimensions of the component are shown here, and the weight of the component was about 1,000 kilograms. For the removal of the specimens, we identified suitable areas with a constant wall thickness. The large specimens were removed from an area with a wall thickness of 36 millimeters. The small specimens were removed from areas with a wall thickness of 18 millimeters. The difference of the wall thicknesses has no significant influence on the mark structure and no influence on the properties, or no significant influence on the properties. The fatigue tests were carried out on an electrical resonance testing machine shown in this picture. The specimen is clamped here. On the bottom we have a load cell to measure the force, and on the upper side we have a swing mass and the cylinder who applies the cyclic loading. The axial fatigue tests were performed stress control with a constant sine amplitude and a stress ratio of -1. The test frequency is dependent on the specimen geometry and ranges from 95 to 145 Hertz. The tests were carried out in air at room temperature. Let's have a look on the results for the large specimens. In this diagram, the nominal stress amplitude is plotted over the cycles to fracture. The 3 SN curves indicate a survival probability of 10, 50 and 90%. In red, we see the curves for the specimens removed from the component. In blue, the specimens removed from the cast samples. The tests were carried out up to 10 million cycles. When this number of cycles is reached, the specimen is considered as a runout and is marked with an arrow. The runouts are then tested at a higher stress level, which is then indicated with this symbol here. However, the runouts which are tested at higher levels are not included in the creation of this S-N curve because they perform better due to the preloading. The S-N curves run up to the knee point with the slopes indicated here, and after the knee point we see a very small decrease in the fatigue strength, and therefore we have a slope of 44.9. Both curves are very similar. We have similar fatigue strength at the knee point with 104 megapascals and similar fatigue strength at 10 million cycles. We also see that the scatter ratio of 1 to 1.1 and 1 to 1.18 is low and very similar. In this diagram we see the S-N curves of the small specimens. Again, both curves are running very parallel, and also the fatigue strength at the knee point and at 10 million cycles are very similar to each other. In comparison to the larger samples, the scatter ratio is increased. Here we can see the S-N curves for the notched specimens. Again, we have very parallel slopes of the S-N curves with similar fatigue strength at knee point at 10 million cycles, and we have a comparable scatter ratio. In this diagram we see a comparison between the large specimens and the small specimens. Therefore we have the S-N curves with a survival probability of 50%. In blue and light blue the specimens from the cast samples, and in red and orange the specimens removed from the component. And we see that the fatigue strength of the large specimens is higher compared to the fatigue strength of the small specimens. At 10 million cycles we see a 40% and 18% increased fatigue strength, 40% for the component and 18% for the cast samples. In this diagram, the local stress amplitude is plotted against the highly stressed volume. The local stress amplitude is the product of the nominal stress amplitude at 10 million cycles and the notch factor. We see here the notch specimen with a very high local stress amplitude due to the high notch factor. Here we can see the small specimen and here the large specimen. The volume exponent V can be calculated using this formula here, and this allows the transfer of the fatigue strength to other highly stressed volumes. At first we see a decrease of the local stress amplitude with the highly stressed volume, and then we see an increase. From here to here we have the statistical size effect combined with the geometrical size effect because of the notch. And in this case we only have the statistical size effect. and we see an increase, which is contrary to the statistical size effect on the fatigue strength and has not been observed for other cast iron materials yet. Bleigher investigated different nodular cast iron grades and determined the curves shown in the diagram here. We first see a sharp drop in stress, and then a flattening of the curve can be observed. But we don't see a sudden increase as we have seen it for the gray cast iron. This brings us to the end of the presentation, and I'll give you a short summary and outlook. The statistical and geometrical size effect on the fatigue strength of gray cast iron was investigated. In the first step, the local microstructure of ENGJL300 was investigated based on cast samples and a serial component. The graphite arrangement was agraph fit. The microstructure was similar. Specimens with different highly stressed volumes were removed and fatigued. We observed that large specimen had an 18% for the cast samples and 14% for the component higher fatigue strength compared to the small specimens. This effect is contrary to the statistical size effect for other cast iron materials such as ductile iron. Notched specimens show significantly higher local fatigue strength, which can be attributed to a very good micro-support effect. In order to verify the statistical and geometrical size effect, further specimen geometries with different highly stressed volumes will be investigated. This will be realized by specimens with different notch factors and by larger specimens with very highly stressed volumes. Furthermore, the influence of the graphite arrangement will be investigated by casting sampled with E graphite. Finally, I would like to thank the German Federation of Industrial Research Association for funding this research project, and I would like to thank our partners for their support. And I would also like to thank you for your attention, and I'm looking forward to your questions at the IGF conference. Thank you very much.